Hello, everybody. I'm Richard Johnson, and yes, this talk today is about a hardware platform feature on Intel processors called Intel Processor Trace, and we'll talk about the internals of how all that works and how to apply it to things like fuzzing. As Belinda mentioned, I am the research lead for Cisco Talos. We're a small Vuln dev team and primarily focusing on finding bugs and doing technology innovations, which is where I focus. This is my third or fourth year speaking at Hack in the Box, so it's great to be back. I definitely do want to highlight that I have a research partner, Andrea Alivi, who's done a lot of this work with me. He's a great kernel developer and helps with the implementation of the driver. We've given this talk together previously, but he couldn't be here today. So basically, my last few years of research have been around trying to squeeze out as much performance as possible during the fuzzing process. And I've had a couple of previous talks that have gone in the directions of looking at various ways of tracing, either using hardware features such as legacy versions of what I'm going to talk about, or using things like dynamic binary instrumentation, things like PIN and Dynamo Rio, so you can hook applications, as well as looking at the platforms and processes and everything from input selection to how to tune your virtual machine so that they're the highest performance available. So if you're interested in this topic, these slides, previous talks are available out there on the internet. My website's moflow.org. It'll be at the end, don't worry. And so this research started just last year, last fall, and I'll tell you about the progression through that. And most importantly, the driver side of what I'm talking about today is available. So the tracing engine that powers all of this research is already available. It's right now on GitHub/IntelPT. And actually, the code that I'm using for the fuzzing side will also be released, if not this week, then next week. Everything is going to be open source here. So basically, our agenda will be an overview of IntelPT, talk about the internals of the driver implementation a little bit. So we're going to get into some Windows kernel programming stuff for a little while. And then there'll be a whole bunch of demos. We've got an IDA plugin and various demos to show you how to use this, and so on. Before I get started, just to get a pulse of the room, can I get a raise of hands? Who's done fuzzing or actively does fuzzing, knows a little bit about fuzzing? Okay, good. And then how many people here have done driver development on the Windows platform or anything along those lines? Okay, so the fuzzing stuff is the second half. I apologize if it gets a little dense in the first part where we talk about the driver, but there will be a good payoff in the end. No spoilers, but this is the fastest engine for doing Windows fuzzing. So Intel Processor Trace. What is it? Well, it's a low overhead hardware execution tracer. It's built into the silicon of Intel processors going from Skylake forward. Specifically, Broadwell forward, but Skylake is the architecture where it's fully baked. Broadwell had a limited feature set. And basically what happens is each core, and including hyper-threaded cores in your processor, have a mechanism in which when the instruction decoder encounters a branch instruction, it goes off and it checks a register in the CPU that you can set from privileged mode, and it says, okay, are we specially handling branches? And if so, how do you want to handle them? And the processor trace subsystem is how that all happens. Inside your CPU, there's something called a performance monitoring unit. You know, similar, just like there's an ALU that does your arithmetic, well, there's a PMU that does your performance monitoring. And most commonly, this is something that you might see that will tell you like things like branch misses or how your CPU is utilizing your cache, simple counters that you can utilize. But there's a whole lot more in there as well that aren't as commonly used. There's some legacy systems, like I mentioned, called like branch trace store and other things. And so the important thing to know is that this is just inside your processor, and you configure your processor in a specific way to turn it on. The properties of the trace, and this iteration of them giving you branch tracing, are finely tuned for performance. So it doesn't have an impact on your CPU cache, and so it's very performant, and the log that it outputs is very small, so it has a small space requirement as well. So of course, we're talking about branch tracing, so what do we use this for? Obviously, code coverage is the main focus here for fuzzing, and then also it can be used in malware analysis and other sorts of things where you need to recover where your execution went on the logic that it followed in the program. So in order to detect if your processor supports Intel PT programmatically, because you can't just trust a Skylake label or something, you use the instruction CPU ID, and CPU ID tells you, specifically what model of CPU you're running. And an MSR is a model-specific register, so each version of the architecture has different sub-features that are accessible from kernel mode or hypervisors to configure the processor running in different ways. The old common one that you may have heard of is, the switch from real mode to protected mode is one type of operating mode. There's VMX mode now when you have hypervisors and so on. So this is in a similar vein where you're specially telling your CPU to enter a special mode. One part that's exciting about this, one of the reasons that I took up the effort to work on this, was that there isn't an available engine for utilizing this on the Windows platform. It is inside the Windows on the Linux kernel side as of like 4.3. If you compile in some special extensions, but on the Windows side there really wasn't anything available. There is Intel System Studio, but they have a WinDebug, a KD plugin for the kernel debugger that will set these MSRs for you, but the way that it's set up is really meant to be a master-slave debugging scenario and not really useful for fully automated back-end engines for unmonitored execution tracing. So that was kind of the motivation here, and then timing-wise, I've been aiming for getting it done right about now because the Xeon CPUs are switching to the Skylake architecture this year, and so now when you go out and you buy hardware to do malware analysis or fuzzing at scale, you can use my software and use this right away. So anyways, as I mentioned, use CPI ID. It looks something like this. This isn't too important, but the point is it's pretty simple. Once you know that you have the right processor, you can query which sub-features of Intel Processor Trace are available, because there's a bunch of them. Essentially, you can trace either user mode or kernel mode. You can filter on a specific process using the CR3, which is your page table pointer. You can tell it that you want to reserve a range of physical RAM that you want it to do like a ring buffer write out to, or you can tell it, hey, no, I've actually created a set of page tables for you so I can grow and still only manage physical memory myself, and so on. So again, there's a bunch of configurations. There's a whole new chapter in the Intel Architecture Manual, actually, chapter 36. It's about 100 pages, and it covers all the sub-features available in Intel Processor Trace. And I totally stumbled across this by accident, but it's hard to miss a whole new chapter in the manual when it's on a topic that you're interested in. So you can do all sorts of things like put out precise timing information if you need to synchronize these, or if you need to pull out, if you're utilizing multiple cores, then each of those logs are written separately by each core, and you might have to synchronize them, and so on and so on. I think I have a graphical version of this in a second. But the reason that we're interested in this for code coverage is, number one, we can trace native binaries, so that's important. We don't need source code to add tracing logic to. It's implemented in hardware, so it's, number one, it's reliable. You don't have to do any sort of graph recovery to do instrumentation or anything related to the software at all. It runs, like I mentioned, in kernel and user. It runs in VMX mode. It's available in VMX mode. No hypervisors actually expose this feature yet, but we're working on that. As of last week, it works. But most importantly, the performance is really good. So the overhead that you see with this is 15% to cover everything going on in your system. So system-wide branch tracing for 15% overhead is more or less unheard of, unless you're able to do direct source instrumentation. And it logs to physical RAM instead of you giving it a user space allocated buffer that then your kernel passes down, and then there's address translation that has to occur to write in that buffer for you. If the implementation takes the virtual memory addresses to write that buffer, well, that means that every single branch, it's going to have to do a lookup from the physical range that it's operating on in the CPU to what that virtual address is, and that pollutes your cache that does that translation normally. So when you're executing code or referencing normal data in the course of running a program normally, you want the most recent code to be in your cache and the most recent data to be in your cache. But if every branch you have to go out and write out to a buffer, well, that's going to pollute your translation buffers and it will flush. So by making the consumer of this tracing engine, like us who wrote the driver, have to handle all the memory management ourselves, it can just say, hey, I expect some physical RAM, and it's up to you to figure out how to do it. And since you're giving me physical ranges, that means that you're ensuring that the OS isn't going to stomp all over it or whatever, and we don't have to do any cache pollution. So it incurs a bigger cost up front to get everything configured, but at runtime, it's very, very fast. And then another annoyance in utilizing it is that the recording format is so sparse. It only records 1 bit per conditional branch, and it records long branch targets. So if you have a far call or something like that, then you'll have some of the actual address in there. But otherwise, you have to do an online disassembly to determine where those branches are going. So again, on the implementation side, it's kind of a difficult thing to do. But at the end of the day, once you get it all configured, you can operate in different modes of filtering. So like I mentioned, either all of user mode or all of kernel mode, or specifically, you can trace a single process using the PML4 page table, which is kind of in x64, it's another root to your page table partitions. Or you can specify up to 4 ranges of instruction pointer addresses. So you can say, I'm interested in this module that's mapped into memory. Maybe I'm interested in these couple of modules, or I'm interested in this kernel driver, and then also the user mode application that's interfacing with it, and so on. So it has some pretty cool configurations. I've added some stuff to this talk, so some of these implementation details around how to set up the memory, since we don't have too many kernel programmers here, I'll kind of gloss over. I got a brand new feature working as of today that's pretty killer. So, but in kernel space, if you want to use it in the simplest mode, and in fact in the Linux kernel, they have an option to always have it on and to always be writing to a ring buffer. So if you end up with a kernel crash, you have that available and it will dump it out. So one way to do that is to reserve a range of physical RAM when the kernel is booting before your physical memory gets fragmented. And on the Windows side, you can do that through allocate contiguous memory. Our driver happens to implement all the features available at this point. So you can use our driver as reference kind of on the internals of how this all works as well. The table of physical addresses, TOPA, is an option for configuring it. And fortunately, it ends up using the same structures that are necessary on Windows to set up the memory descriptor lists that it uses for virtual memory addressing. So it turns out to be fairly easy. Intel made it as easy as possible, knowing that we're going to have to do all this work. And this is the mode that we generally operate in. There is a small runtime hit because it has to do page table walks, obviously. But at the end of the day, you can make your logs as large as you want them, as much virtual memory as you need. And then, of course, we get interrupts whenever that's full, and it lets us dump and parse everything. So the packets of interest are, I'll just give you the visual version. On the green ones are the taken, not taken, and taken IP address. So these are your branch targets, or whether or not your conditional branches were taken. The F updates is the frame updates. Then paging in packet, so that's important if you're tracing multiple user processes and you want to know when a certain process gets paged in and is activated. And so on, if you're in ring 3 mode or in ring 0. And then there's some timing stuff as well. And then the PSB and OVF, those are synchronization packets that are in there. So it allows you to seek ahead. So for our driver, we've released a number of versions over the last almost year, I guess, only since May. Yeah, almost a year. And at this point, in our first version, it only supported the single buffer, and it was really weak. But right now, it's fully working, fully baked pretty much. We're on version 5, or 0.5, but there isn't really anything left to implement right now, other than some testing. We support multiprocessors, all the filtering modes and output modes. And in the last 2 months, the things that we've added are the kernel mode tracing, and also you can utilize this from another driver in kernel mode as well. So I have a user mode library that I use to interact with it, with our driver via ioctls. And then now there's also an API exposed from the kernel side to utilize it as well. And then there was some low-level stuff that we had to manage along the lines of how to map those buffers and the APIC programming, which is how all the interrupts are handled outside your CPU, and so on. So the performance monitoring interrupt is a special interrupt, and in hardware, basically the way that you do asynchronous notifications are via interrupts. And so when we put the CPU into a mode to log all your branches, we say, go ahead until either we tell you to stop or certain conditions arise, such as the buffer being full. And when the buffer is full, we want to be notified, so we have to register a callback in the kernel that listens for a particular interrupt to let us know that it's full. So in order to do that, we had to jump through some hurdles that I will partially skip over, but basically you can use the HAL set system information API, which is pretty much undocumented, but you can grab the APIC interrupts address out of there and then register your interrupts address with it. And then of course, this is running at a super high privilege level, and so in order to be able to communicate, you need to use things like deferred procedure calls and do things asynchronously. It's like a whole bunch of layers of indirection. So for the user mode buffer that you want to finally get back, so the way that we utilize this right now is we have a controller application or what have you, and then you have your target application that you want to trace. And we need to have the buffers that you want to parse and utilize mapped into that controller application. Because if we map it into the target application and we end up with a crash or something, if we're fuzzing and we're trying to cause crashes, well, if that crashes while the CPU is locked pages into RAM and is expecting things to be there, well, if your process dies, then all of a sudden the kernel tries to clean up those pages and your CPU shits the bed, and that's no good. So in order to do that, we set up these page tables and we tell the interrupt handler to tell us when it's full, and we use the Windows memory descriptor list APIs, and we lock it in there with map lock pages, blah, blah, blah. For the multiprocessor and multi-threading support, we just had to add in a layer of abstraction that essentially has specialized structures that handle all the configuration for this. And then, of course, we had to be able to handle the interrupt and determine which CPU core it comes from. And then right now, the last stage, which was actually advertised on the abstract but turned out to be a rabbit hole that didn't pay out, was we were trying to figure out how to separate user mode threads, which are a completely different abstraction than your hardware threads, so that we can say, I'm interested in Internet Explorer, but I'm only interested in the thread that's doing JavaScript parsing or interacting with the DOM. Or maybe that's a bad example because they spawn asynchronous threads all the time, but maybe you're interested in any larger application, but really you only want to follow the parser threads. And as you'll see here, since that log format was so compressed, there's a lot of work in decoding it. So the more work we can take away from us, the less data that we have to parse and translate back into actual branch addresses, the better. So we went down the route of doing Windows event tracing, ETW, and had to do some reverse engineering of how that all works on the kernel side, because you're supposed to, generally, you're supposed to define what you want to trace. So we wanted to trace the context switching of the Windows kernel. And so normally what you do is you give it an XML blob and it generates code for you and says, okay, use this library. This library will now tell you whenever a context switch happens. Only a context switch isn't actually one of the things they let you do. And then we needed to do this from the kernel mode side. So long story short, we went through about a couple of weeks of implementing that and reversing it. And then we realized, shoot, that's all asynchronous. And so at the end of the day, we were notified that thread had switched who knows how many milliseconds ago, and so that desynchronized our logging and so on. So that is the last remaining issue to solve, which is probably going to be solved through APC, but that's neither here nor there. So the kernel mode tracing I'll be able to demo for you. It's actually really cool. We can trace our own driver because all the tracing is happening from the CPU. So there's no issues like if you want to kind of self-trace or trace any arbitrary code running on your kernel. Of course, the way that you interact with our driver is that we have a named pipe that you interact with, and you set ioctls down there. And naturally, you need administrative privileges because you wouldn't want a low privileged user to tell the CPU to start tracing a high privileged process, and so on. But yeah, so now we can trace kernel module loads and unloads and all the things going on inside and so on. I'll demo that here in a little bit. And at the end of the day, it's abstracted fairly well. I have, as I mentioned, a library that interfaces with this. But generally, it's as simple as you get a handle to the device that we expose, and you interact with it through some ioctls to start the trace, and then you can stop the trace and then query, how many packets did I receive, and so on. And this is probably not too important for you. There were some other tricky issues making the page tables not get swapped out and yada yada. But let's go ahead and just look at some stuff here. Let me fix my mirroring. Sorry, as I mentioned, I was working on a new feature that is kind of the exciting addition for this version of the talk, which will be the last version of the talk. And so I didn't get a chance to fully get my demo set up ahead of time, but this isn't so bad. Okay, so generally, we install a service that controls the driver. So the driver right now, since I was already doing some testing, is compiled and installed. We have a demo app that we ship with it. Let me make this so it's not on the bottom. Just make this a little bit bigger for you. Okay. So, is that too big? Okay. All right, so first we'll do some user mode traces. We can do something as simple as Notepad, and how many processors do we want to run it on? We'll just do it on the one for the moment. All right. Of course, we get a nice unknown error. Okay, so basically, to give you an idea of what we're dealing with here, the output is this, this binary format that's not at all useful to us unless we decode it. Fortunately, I'm not sure what the heck, okay. So Intel ships a library called libipt. And so this is the output format. Obviously, it's a binary format. Has all those packets exposed. We're able to dump that to text to give you an idea of what we're actually looking at the contents here. So these are those packets that I just shown you. So the PSB is kind of like the start. This is a taken IP packet. And so we can see that we do have some long branches here, so we can see the full physical address, or full virtual address rather. And then we see things like taken IP, no idea, taken IP, but only the low word. Then we have things like the taken, not taken. And The taken not taken, you'll notice, has these exclamation marks and dots. And so those are determining whether or not that branch was taken or not. And so it codes up to 6 branches into a single byte. The other 2 bits are used for the actual packet ID, and so on. So this is what we have to start with, and then naturally we need to determine what those branch targets were, and the taken, not taken, and so on. So let's look at this in IDA. Let's go ahead. All right, so this is Notepad, and we will go ahead and run our IDA plugin here. All right, and it should. Probably should have run this against something with symbols, sorry. I'm not sure it actually loaded that file properly. Yeah, it didn't. Okay, let's try that again, sorry. This has been a moving target because every time I give this talk, it's a totally new version of the code, and obviously we get desynchronized a little bit sometimes. Maybe I'll just jump to the kernel one that has symbols, so it'll be a lot easier. Sorry about that. Yeah, let's do the kernel trace real quick, just so that we can get back on track. Okay, so now it's tracing in the background my actual driver itself, which I think I have symbols compiled for, so we hopefully will be able to see here. Let's verify this. Okay, yes. And here we can see, obviously, this one's even a bigger pain because it has a lot less full addresses that you can utilize. So let's try that one more time. All right, yes, so this time we have symbols. So we should have better luck here. Shit. I'm having an issue parsing the file here, unfortunately. The IDA plugin's probably out of sync with the parser on that we're emitting for the output. Basically what you normally would see here, I've got more demos that you guys will enjoy, but what you'll normally see here is your typical overlay with highlighted blocks, and then it will actually deepen the color. We use blue, and it gets darker blue for cycles. So it's immediately obvious when you get the cycles. Man, that's a real bummer. If we have time at the end, I'll come back and do this one again. I don't want to waste too much time screwing around with this one. So yes, let's get back to the slideshow. So, okay, so we have a fast tracing engine, 15% overhead. We're recording all the branches. You'll just have to trust me that we're decoding them properly for the IDA plugin. So how do we utilize that for Vuln discovery? Well, so evolutionary fuzzing is more or less the hot sauce going on today. It's incrementally better mutational dumb fuzzing via using a feedback signal, which of course in this case is code coverage, so that we can determine did the newly generated input reach new parts of the code, right? And so basically we use code coverage, and then we basically use the code coverage as a fitness function, which is what you would use in genetic programming, and then we also utilize that over time to determine each new input. It's interesting. From my last couple of years of talks, the required components in order to do this effectively is we need a fast tracing engine, obviously. The slower your tracing engine is, you can't execute many times a second. We need block-based granularity as opposed to something like function coverage. The early research in this space was Jared DeMott and the EFS evolutionary fuzzing system from like 2006 or so. He did it for his PhD, and he really dove deep into the science of how genetic algorithms work and what fitness landscapes there are, and what attributes you can put into it. But at the end of the day, we need to minimize the attributes that we're looking at because we need to do very, very fast lookups and references across your entire population pool, so your entire corpus. And in order to do that, we need data storage that is very efficient to do comparisons over time. And so American Fuzzy Lop is the fuzzer that people have been using the last few years, developed by Michael Zawiski, who's done a lot of great work over the decades. And it was originally designed as a fuzzer for open source software. It operated by modifying the assembler output of GCC and annotating it such that you could do call-outs to your coverage function. It implements a variety of traditional mutation fuzzing, so you're flipping bits or bytes or words, or kind of taking half of two files and merging them together and so on. It has a nice catalog of different types of mutations. And then using the GCC, or using the modification on the assembler emitted by GCC, then he compiles that. So instruments the .s file, the intermediate file, compiles that so it's baked in. And then most importantly, probably was to track it over time, he uses a Bloom filter, so you can determine whether or not you've traversed this edge from block A to block B previously. And if you're not familiar with the Bloom filter, it's essentially a lookup of a map. In this case, he uses 64K of RAM, which happens to be the size of an old CPU cache. Modern architectures have 128K now, but 64K for the cache because you're hitting it on every branch. And he takes the previous basic block's address and the next basic block's address and does a simple hash by shifting the high bytes off and XORs them together. And so then you end up with this, this one 64-bit value that represents an edge transition. And then modulo the 64K map that he has, he indexes into that, and then increments that offset. And so that's how many times you've traversed this particular edge. So that happens to be a really, really efficient, both in space to store all that. So previously, if you looked at block tracers, what they would normally do is record every time you enter a basic block, either in a text or binary format. You end up with a list of blocks, and then later on you have to figure out how to do a diff across those executions. So this kind of keeps that state all in one 64K blob for you. And then not only does it keep a single execution, but of course you can keep over time the entire corpus's state as you've gone through them. So it's very, very trivial to determine if this new execution that you just did has incremented any of those bytes in the map. So very useful and very, very fast to do comparisons on. And then, of course, this was written using POSIX API and so on, and what we're interested in is applying this to Windows. So I think I covered all that. Oh, also, fork server was another important addition that he used for performance. Architecturally on Linux, when you create a new process via fork, it uses copy on write on the memory pages. So it's very, very fast to initialize a new process. It's a matter of copying page tables. So rather than having to do a lot of work to initialize and reload and remap all of your binaries, it's using the already mapped physical memory and just copying the page tables over so your new process points to the same thing. And then you can do nice fancy tricks like wait until a little bit later in the process to do your forks, so you can skip all the unnecessary code before your input is seen and parsed. All these things are great performance additions and very, very important to the architecture of a fast, modern fuzzer. And the kind of a keynote here that Ben Nagy originally pointed out is that when we're fuzzing complex, large targets like you see commonly on Windows, you can still use these efficient fuzzers to generate corpus. So if you want to go fuzz the PDF library in Windows, the new one in Windows 10 and Edge, that's actually really difficult to instrument. It's slow, it has an asynchronous API, there's all kinds of complications around it, but you can take American Fuzzy Lop and point it at Poplar or any other open source PDF library, and it keeps the corpus. It keeps every unique input that it saw take a different branch in the open source version. So you take all those over, and then that's where you start fuzzing on the Windows side. So that's just a little side note. But some fuzzers don't keep the entire corpus. They only keep the crashes. And actually a lot of value is in those unique inputs that you can then use as inputs into other parts of your workflow. So yeah, we covered that. So on the Windows side, I started looking at this RuxCon or so in 2015, and initially my tests were actually on the Linux side, since I noticed that this feature was in there, and then when I was looking if it was available to use via software, I noticed that Linux had it available. So not only does Linux have it available, but I actually used a reference driver that's available from Intel. It's on GitHub called SimplePT, written by Andy Clean, who also wrote the other PMU tools available for Linux. So I started off on that direction, and just to see what kind of performance we'd get out of it. The performance was sufficient enough that I decided to go on this kind of long trek and trying to implement this on Windows. And naturally, the biggest problem on Windows is that we don't use a lot of open source software, or at least the software that you might download from vendors is the open source stuff will be baked into other binaries and so on. So we really do need a binary tracer to work on this. And while I was thinking about this and how to move to the Windows platform, it turns out that Ivan Fratrick from Google was also on the same track. And not on the Intel PT side, but he just clearly identified that AFL is a great fuzzing engine. Wouldn't it be great if we could get this on Windows? And he happens to work with Zelewski, so that was kind of a natural thought process, I'm sure. And it's available now. It's American Fuzzy Lop. It does work on Windows. There was quite a bit of internals that had to be modified, since Windows is not at all POSIX compatible. And then, of course, you had to choose a tracing engine that will work against binaries. In his case, he chose Dynamo Rio. And the implementation on his plugin is actually excellent. And if you look at my previous talks, I really dissect the differences between Pin and Dynamo Rio, Valgrind, and so on, and why you should choose one over the other. And my conclusion there was that Dynamo Rio is the better platform if you need performance. And the primary reason is because on Pin and most DBI platforms will allow you to insert hooks out to a callback function. But Dynamo Rio actually lets you synthesize instructions directly within the basic blocks. So you can do, and it also supports small static analysis. So it can do a liveness analysis on certain registers within that basic block. you can determine that, oh, well, this is a dead register within the block, so I can use it to implement, a faster table reference, for example, rather than calling out and doing cache pollution that way. So it's one of the prettier DynamoRio plugins out there. It's worth studying for that alone. It's good code. But yeah, so he's using DynamoRio. You can filter based upon which module you want to do code coverage on, because DynamoRio is good. It's fast for a DBI, but it's about 30 times slower than native execution or so. So you want to limit the code that you're tracing. And then I recently actually had a chat with him, and we kind of fixed the multi-threading edge coverage, but it has a block mode and an edge mode. Essentially, the solution for doing the edge tracing across threads is to use the thread local storage to store your last branch. Otherwise, if you get interrupted and another thread's executing, you have a fake edge that doesn't actually exist. And then the biggest part and the most important part is that he does persistent execution, meaning that he's doing in-memory fuzzing. And this is important in particular with DBI, because the way that they work is they're a custom loader for your process. And when you run your process, the DBI loads it and hooks every branch, if you register branch callbacks, and it has to disassemble that branch each time it discovers a new one. And so naturally, every time you restart a process, it has to do that all over again. These aren't being cached to disk. DynamoRio does have a flag that's meant to cache its instrumented basic blocks to disk, but it has issues, and in reality, it isn't fully there. So Ivan took the persistent mode approach, and the idea is that you pass in an offset into a module. The module can be your own module that you wrote that's a wrapper for an API, which tends to be the right way to go if you can, or you can specify an arbitrary offset into an application or arbitrary DLL that's a function entry point, and you tell it how many parameters are passed to that function, and then it's able to use the DynamoRio API to wrapper that entry point and do a loop for n number of iterations before exiting. So this works out to be really good and very performant, better than anything else that was out there on Windows. And for example, since we're using DynamoRio, if we restart the process every time, which essentially disables the persistence because it's not doing in-memory fuzzing, it takes a half a second at least to do their demo, which is a wrapper for GDI+. Now, if we enable persistence mode, then we get a much healthier 72 executions a second, and that kind of tops out somewhere around 1,000 iterations just over 100 executions a second. So this is good performance. It's not quite where we're at on the Linux side with being able to do source instrumentation, which might be triple or up to 5 times that speed or so, but it is quite good. And really just the key takeaway here is that persistence is the key, particularly if you're using DBI. So where did we go with this? Well, we use our Intel PT driver. I wrote some code to wrap that inside of AFL, and initially we have all these problems that we have to solve. The block IDs aren't available, so I had to figure out a way to, obviously I had to disassemble online and then build your own cache for those branch targets to do it efficiently, and then ideally save that out to disk. The larger the file is, the log file, obviously it takes a while to do that parsing, so we want to limit the amount of parsing we need to do. Previously, this third point said that persistence wasn't implemented yet, but that's the new big feature as of today. And we can limit the code that we're tracing down to 4 ranges that are available and supported by the hardware engine. So the current status is now we accurately decode the full trace. The taken IP packet, of course, holds the target address, and we get that for the indirect branches in return. We disassemble the taken, not taken packets and have a branch cache. And then, of course, we use that. We have to come up with our own little way to encode it into the Bloom filter since we have full addresses and not block IDs, but that's fairly simple. And, of course, since we don't have fork, we need to use create process and wait for single object, just like you normally would. I did do some research. We did try to implement a native Windows fork using some undocumented APIs called NT or RTL clone user process, and went down that path. We got it working. The only problem is that these are NT subsystem APIs, and they're not aware of the Win32 subsystem. So basically, anything that links against user32 and CSRSS is not aware that your process exists, and so it was kind of a chicken and the egg thing. We could compile libraries, especially not to link against user32, and do that and have fast forking, and that was all great on our own wrapper. But the default compile flags for Visual Studio, the ones that all software are going to use that you will see, I mean, you'd be lucky to find any program out there that doesn't link to user32. So unfortunately, that ended up being a fun little journey down a rabbit hole again that didn't pay out, but it was interesting research. So previously I was comparing my performance, iterating each time, creating a new process, and fuzzing against it, and I'll show you those numbers in a second. But as of today, the native persistence mode is now implemented. I don't have a lot of slides to describe this to you, so I'll just kind of do it verbally. Alex Ionescu last year at Recon gave a talk on various modes of Windows hooking that are built into the system, and one in particular that's interesting and may now be on your radar as of the last week or two is the application verifier DLL hooks. They're relevant again because some cyber company out there thought that they invented some new malware technique or something. But so now I don't know. I chose this approach as opposed to just doing DLL injection because I figured, well, I want to run this on systems that might also have anti-malware software running. Didn't want to cause issues and flags with that, so I figured, okay, if you're going to use something like PageHeap in Windows, the way that it's utilized is via the application verifier infrastructure. And so I was like thinking that would be a great system-supported, undocumented, but system-supported API for doing DLL injection. So that's what it uses. It's pretty cool. Maybe I'll pull up that code in a second. But you can define some structures that say, I'm interested in hooking this export from this library, and all you got to do is define a couple of structures and your hook function, and it's done. Turns out that, and I also needed to do raw hooking as well in order to do like, arbitrary function hooks and so on, your actual wrapper hook. And so I ended up using DieStorm X, which was just released last summer by the author of DieStorm, which is separately, I've done some research on various disassembler engines, and DieStorm is actually twice as fast as Capstone and more accurate. It's the fastest and most accurate disassembler out there. So that's the one I favor. And then there needed to be an IPC channel when you're doing the persistence mode, because now instead of just waiting for a process to exit, you need to be able to notify the fuzzer that, okay, I did an iteration, I'm back to the wrapper function, I need a new input to be generated so I can do it again. So there's a small little IPC mechanism using name pipes as well. And so what does this all look like? So in order to do some raw performance testing, I figured the first thing that we should do is figure out what would be our create process and wait top end before I got to the persistence side. So in this particular demo, the one that comes with WinAFL, the GDI Plus wrapper, I was able to only create 85 processes a second that were loading and parsing a file. And that's without tracing whatsoever. That's literally just a tight loop, create process, wait for single object, parse a bitmap file using the GDI Plus API, the 2 API calls. So then I enabled the Intel processor trace without logging the output, just to see, okay, what is the runtime hit that we're getting here? The docs say they should be about 15%. Is that what we're seeing? So yes, in fact, it was almost exactly 15%. So we went from 85 down to 72 executions a second. All right. So then we add in the parsing of that log file with the binary logging, and we're down to 55 executions a second, which was another 22% parsing overhead. So in sum, we hit about 35% overhead on doing the Intel processor tracing and starting a new process each time, which turned out to be slightly slower than the WinAFL version, which I used to have in the slide, but it got moved out of here. But basically, they were hitting closer to like 80 executions a second, and I was getting 55. So that's where basically the talk was ending. Last time I gave it. Except there are some gotchas, because Dynamo Rio has a variable performance depending on how much code it has to disassemble and what it takes to bring that process online under the DBI, whereas Intel PT has a reliable 15% decode overhead. So I decided, okay, well, they use a GDI plus wrapper. Why don't I use libpng or something? And naively just wrote a simple PNG parser, and I was like, what the hell? This went down to half an execution a second versus what I was getting with Intel PT, which was like 64 executions a second, and that seemed weird, so I pinged Ivan, and I'm like, hey, that doesn't seem right. That's 100 times performance difference. Well, it turns out that there's a lot of gotchas when you use something like Dynamo Rio. This turned out to be an issue with file descriptor management, where, and Windows file management is a pain in the ass. But long story short, that's not an accurate representation. Once I modified some stuff a little bit, they were back on par. So it was up to me to say, all right, we're finally going to tackle this persistence problem. And so I'll demo that for you. But what we should see is we're now 5 times faster than the current version of WinAFL. So if the demo gods are with me on this one, we'll at least get to see that. So first, let me show the Dynamo Rio version. All right, this one should. Okay, yes. Okay, so this is a live version. This is Dynamo Rio tracing the GDI plus. And we're seeing this will climb a little bit over time as the cache gets hot and so on. I think this actually does top out closer to 65 or 70, but as you can see, pretty obviously, the performance is in that range. And as of today, some of the changes that I had to put in here that obviously screwed up some of my other demos. But yes, so now we're seeing that with live Intel PT tracing, using persistence mode, in-memory fuzzing, we have 230. This actually will get to like 260 as well. So we got like a 5 times performance increase. So that's the main new thing here today. So the driver is open source right now. This code will be open source soon, and it will have advanced performance against Windows binaries by 5 times. Yes, thanks. So the conclusions, takeaways here, tracing is used in fuzzing dynamic analysis. We have all kinds of applications for doing the branch tracing. My particular application today is fuzzing. Yours might be doing malware analysis across a billion or a million samples a day or something. It's definitely a promising iteration in hardware-supported tracing. It's like 30 times faster than the previous generation of supported tracing, if not more. Which tells us that Intel is actually dedicated to producing, more interesting, dedicated silicon for doing things like security analysis and so on. My hope is that someday they will put some sort of data flow tracing capability into the processors so we can do things like online taint tracing that are efficient and so on. So we'll see if we get there. So the to-do list, number 1, we tried that, we finished that, it doesn't work, so that's not the right way. But the right way is probably using asynchronous procedure calls, which allow you to preempt thread activation with your own custom function. If I was thinking like a malware author, I would have done that first, but I was thinking like like an antivirus author, it went the other way. So yeah, that wasn't good. The hypervisor support on this, as I mentioned, when your CPU is in VMX mode, hypervisor mode, it is supported. Now, none of the hypervisors currently available, Zen, KVM, VirtualBox, Hyper-V, none of those support it at all. Only one of those even supports the legacy BTS mechanism. But the good news is my research partner, Andrea, he actually has written a module. It turns out that Hyper-V is pluggable. He's going to be giving a talk at Recon, just got accepted today, that goes all into the sub-architecture of Hyper-V. And he actually has now got this working like last night so that we can trace guests from the hypervisor, which is great. That was kind of the last piece to scale this out. So that will be on your radar this year. We have heard that SMM code should be traceable with this as well, which is very intriguing. However, Diolek and some other guys said that it might require an Intel-provided certificate, so we may never get there. Oh, and then number 4, I can check that off the list too, so that works now. All right, so this code, github/intelpt. This talk and all the other talks related to it are at moflow.org. You can reach me on Twitter at Rich in Seattle. Andrea's the other one. And thank you for listening. I'll take any questions.
Any questions from the floor? Or maybe questions off the floor. Thank you very much, Richard. Yeah?
We're good? Okay.
Yeah? No questions? All right.
Thank
maybe
you.
During the breaks. Thank
Also,
you very much.
also, sorry about that first demo. I have the video up from my talk at CanSec West. It has those demos available. And since all this code's out there, I need to write a blog post that'll show you how to do it. I apologize. Clearly, the driver is working with the fuzzer. I modified it and fucked it up. But thanks again.
All right. Thank you. Thank you very much, Richard.